Good morning, good afternoon, good evening, and welcome to AI for Good. My name is Bastiaan Kwast from the ITU, the International Telecommunication Union, and it is my privilege to introduce today's webinar, Explainable AI and Trust by Grégoire Montavon, as part of the Trustworthy AI series hosted by Wojciech Samek. ITU is the United Nations Specialized Agency for Information and Communication Technologies, and is also the organizer of AI for Good, together with 38 sister UN agencies, XPRIZE, ACM, and co-convened with Switzerland. For today's webinar, we'll be using the Q&A functionality for an engaging discussion. So please make sure to use this to enter all your questions. You can find it at the bottom of your screen. Additionally, there is the chat functionality, which you can use to communicate with other participants. Please make sure to select your message to be sent to all panelists and all attendees. And you can select this just above the message box. With that, it's now time for me to hand it over to our host, Wojciech. Hi, Wojciech, how are you?
Hi, I'm doing good. The weather could be better though here in Berlin. Yeah, so I'm very happy to host the workshop series about my favorite topic, Explainable AI, today. And it's a great pleasure to introduce Grégoire Montavon, one of the pioneers and one of my closest collaborators in this field. So Gregoire is a senior researcher at the machine learning group at TU Berlin and also PI in the Berlin Institute for the Foundations of Learning and Data. So he did his master's degree at EPFL in Lausanne and finished his PhD in machine learning in Berlin here. So with that, I would like to hand over to Gregoire and hope you enjoy the workshop today.
Okay, so thank you for the introduction, Wojciech. Can everyone see my screen?
Yes, we can see it. Thank you.
All right. Yeah, so I will present some of our work on explainable AI and also present how it connects to trustworthy AI. And this is the work of a number of people which I'm presenting. Many of my colleagues at TU Berlin, as well as Heinrich Scherz Institute. And yeah, so the first question we might ask is why do we need trustworthy AI? And basically, we would like to be able to use AI to perform autonomous decisions so that we don't need like a permanent human intervention. It can save a lot of time. And at the same time, we also want to be able to perform high-stake decisions. So decisions that really have some importance from a practical perspective. But the problem is that if you at the same time want to do a high-stake decision, but you completely delegate the decision to the machine, there might be some dramatic failure cases. So to avoid that, it's important to get something to get more trust into the AI model, that we know that even if we are not looking at it at every prediction, we know it will perform well and not fail in the most important cases. So now let's look at machine learning decisions. Basically, a lot of AI systems now incorporate machine learning, and machine learning has a very specific way of producing decision. It does not build the decision function by hand, as it used to be the case before machine learning. Instead, it starts from the data. So basically, we collect some data, and then we assign some labels. We say, okay, this is, for example, for these cases, this should be a positive decision. Here it's in green. And for some other cases, this should be a negative decision. And then we train the model to learn a decision function that reproduces these labels that we have given to the model. So this is a very different way to set the function at hand, where we have full control over the decision function. Here, we strongly rely on the data. And the question now is, can we trust machine learning models that are predicting based on the data? And let's look at an example of a machine learning model which has been trained to detect horses in images. And here, this is a simple bag-of-word classifier. It's composed of 3 layers. And once it has been trained, basically the model performs as a black box So we give some input images, and then it tells us horse or not horse. And we can apply this model several times. And if it has been trained well, normally it should, whenever you give an image of a horse, it should predict horse. And this is also what we could observe in the case of this model. And then there are some standard validation techniques that we can use, which basically take the data, split it into some training data, which we use for training, and then test data, which we use basically for evaluating the model. And you can look at the prediction accuracy for different classes and on the models that we have trained. There are some classes that are very well predicted. For example, cars are detected with 80% accuracy. Same for horses, train in person even more. And basically, based on this number, we would believe that these models have been trained quite well at predicting these classes, and that we might use them reliably on new examples. But now there is an experiment we can do. We can try to take the prediction and reverse the prediction to arrive back into the pixel space and see basically which pixel the model has used to produce the horse prediction. And if we do that for this model, which apparently was performing well on the class horse, we see something unexpected. And here we see that a classifier predicts based on some artifact. If you look in the bottom left corner of the image, you see a copyright tag. And basically, whenever there is a copyright tag, the classifier thinks it's a horse. And we also call this effect clever hands. And Clever Hands is a famous horse from the beginning of the 20th century, which actually was fooling people to believe he was making arithmetic calculation that were presented to him by his trainer. But in fact, the way the horse was able to predict the outcome of arithmetic calculation was by looking at the imperceptible cues that his trainer would involuntarily leak. For example, he would show some excitement when the horse would arrive at the right results. Now, why did this copyright-like artifact happen in the first place? And if you look at the data, you see a lot of images of horse with this copyright tag. So in fact, the classifier, being rather simple, composed only of a few layers, found it was much easier to detect the class to do the prediction task by simply looking at the copyright in the bottom left of the image. And we call that a spurious correlation, meaning that both strategies are valid to predict correctly horses on the training data and in the available data. But then the question is whether this classifier will generalize on future data. And here we can make an experiment. So you take the classifier, and you take the image of a horse, and then you remove the copyright tag. And for some images of the horse, removing this copyright tag makes the classifier believe it's not a horse anymore. And we can do another experiment. We can take an image which is not a horse, for example, this image on the right with a car, and now you add the copyright tag. And interestingly, the classifier now thinks that this image has a horse in it. And this will typically happen in future data. So it's just like a kind of occasional that the classifier, the training data or the data sets that we've been used to train the model had this copyright tag for the class horse. It was just like an artifact of assembling these data sets. People who assembled it took images of the class horse from a certain data source, and it turns out that this data source had this copyright tag. When we apply it on future data, data sources might change, and basically these things become uncorrelated. And so, as a reason, the Clever Hands models, which use this strategy for predicting, are unlikely to perform well on future data. Okay, but how did we get these heat maps in the first place? And it turns out that computing explanations that basically highlight which pixels are responsible for the prediction is a non-trivial task. And the reason for that is that the machine learning model is just trained to output a prediction, but it has no intrinsic self-explainability. So if you would like to explain the model, you need to somehow go backward into the model and manually try to identify what were the important pixels. And this is an area of research that is known as attribution techniques, which is a subfield of explainable AI. And fast progress has been made in this field. And one technique that we have developed for extracting these explanations is layer-wise relevance propagation. So this is basically an overview of layer-wise relevance propagation. So the idea is that you start at the output of your model, for example, a neural network. And then at the output, basically, there is a score indicating the evidence for the class of interest, which might be the class horse, for example. And then you say, okay, I will move layer after layer from the top layer until the input pixels and progressively redistribute this score on the intermediate neurons. And basically, we call this quantity that we redistribute progressively layer after layer relevance. And relevance means basically whether a neuron is relevant for the classifying a given image as a horse or not. And how do we compute this relevance score at each layer? We use a propagation rule. And this propagation rule basically is a function that takes Rk, which is the relevance at the layer L+1, and then compute Rj, which is the relevance at the layer L. And there are many such rules that are possible. And we found out that using specific rules for each layer gives a good result. And it arrives at some explanation that makes sense for the human. An advantage of layer-wise relevance propagation over some other methods is that it runs in the order of a single backward pass, which means that we don't need to evaluate the function multiple times. For example, we don't need to test plenty of perturbation of the image to characterize the decision behavior. We just apply it once. And this will prove to be very useful later on when we want to compute explanations of a large number of data points. Okay, so we have this propagation rule, and initially we've been basically designing them in a heuristical manner, basically based on intuition. But the question is whether this process can be justified theoretically. And a bit later, we developed a technique called deep Taylor decomposition, which provides this theoretical framework to think of LRP. And this is basically the idea of deep Taylor decomposition. We assume that our prediction has been propagated up to some layer L, where we have the relevance score Rk. And now we ask the question, okay, how do we propagate this relevance on the layer just below? And the way we think of this problem is as a function which maps the activation in the layer below the relevance in the layer just above. And now we will try to analyze this function. And specifically, we will perform a Taylor expansion of this function. And the nice thing with the Taylor expansion is that it gives us basically a decomposition of the outputs of the function in terms of individual terms. And these individual terms basically link the function to every input variables. And basically this individual term inform on how we can redistribute this relevance score Rk on the neurons in the layer before. So this is like one step of deep Taylor decomposition, and then we can just repeat the process one layer below, and we just iterate until we reach the input pixels. Empirically, we've also observed that LRP is more stable than methods that are based only on the gradients. So there is something that we observe is that the networks are so complex that the gradient tends to become highly unstable. And here we have an image which is of the class viaduct. And you see that the explanation based on the gradient would produce very noisy attribution, while LRP more robustly highlights what are the relevant features. Here it's this arc just below the bridge. If you look at the function of a deep neural network, what it typically looks like, it's a function which is rather confined in some envelope, but very small high-frequency variations. And this very small high-frequency variation do not really affect the function score. So this is the reason also why you have a good prediction accuracy with these models. But it actually affects a lot the gradients, because the gradient basically turns positive and negative very rapidly. And basically, this is one of the reasons why gradient explanation have so much noise compared to how well the model performs at prediction. And we have been, basically this LRP technique, we've been testing it mostly on images, but the idea is quite generic. So it only assumes that you have a collection of input features and that you then want to take your output of your network and redistribute it on these input features. These input features might be pixels of an image, but it might also be voxels of a volume, and you have this kind of data in the medical context. You might also have some kind of video data or a sequence of images data, like in video games. Input features might be text representation, typically word vectors, as well as speech. And in every case, you can apply the same ID and then highlight what are the relevant features for a given prediction. Also, LRP was developed for different models. So originally, it was proposed for bag-of-word and deep neural network classifiers. I showed a few examples. But recently, we also extended the idea to anomaly detection. So we can take a model which does not classify, but which predicts whether a data point is anomalous or not. And we can highlight what are the features that contribute the most to anomaly. For example, here in this image, it highlights the artifactual stroke that you have on some of these digits. We've also been extending LRP to similarity models. And here you see, for example, two cats and an explanation of why these two images are similar. And basically, here it does not highlight, but it draws a connection between a different pixel of the two images. Sometimes the task requires different type of explanation. In the case of similarity, it's basically a matching task, so it's more intuitive to think of explaining in terms of finding what has been exactly matched between the two images. And this extension is called by LRP, in the sense that we have two branches of LRP running in parallel to perform the matching. And finally, we've also been applying LRP to a graph neural network, and we had an extension that would not decompose only in terms of nodes of the graph, but describing what are the relevant walks in this graph. And with this enhancement of LRP, you can also revisit a little bit the problem of image classification and arrive at more detailed explanation of why something has been predicted in such a way. So here we have a network that takes an image and predicts the class dumbbell. And here we see basically a different layer, what is the process which is used to arrive at a given classification. And you see that basically these arrows that are progressively converging, starting to detect edges and then converging on the object. So that was for presentation of LRP in general. And now we go back to our original problem, which is to try to validate a model, try to make it more trustworthy. And we've shown basically this example of a horse, which basically gives a motivation for using explainable AI technique for validating a model. But here we have just chosen the right image, the image with a copyright tag, and explain it. But if we have a large data set with many images, and some images, of course, do not have copyright tag, and there might be many other classes, we cannot go through all images and compute an explanation. So instead, we would like to have a way of systematically identify this clever hands effect from basically in the whole data set. And we've developed a method for that, which is called spectral relevance analysis. And here, basically, it's composed of 2 steps. In the first step, we compute an explanation for every example in the data set. So we have basically all your data points that have been classified, and we just explain them one after the other, and we get a very large collection of explanations. So here, it is too difficult or too much work for a human to look at every individual explanation. So then we apply a second step, which is to organize this explanation into clusters. And here we make a distinction between clustering images and clustering explanations. We don't cluster image here, we cluster explanations. We would like to have a summary of the decision strategy and not of the data set. And what we get if we do that is basically this different prototypical strategies of the network for predicting. And you see in the first cluster, for example, it looks at the horse, so which is the expected decision strategy. Then in the second cluster, we see our clever hands artifacts strategy, which consists of looking at this copyright tag. And then we see something else that we haven't seen yet, which is in the third cluster, a reliance on the horizontal poles of horse racing, which are also useful for detecting horse. Here, it's not really a clever hunt because it's a useful features. Indeed, horse and these poles are co-occurring in many contexts. And then you have the fourth cluster, which is again one cluster which looks at the copyright tags. And so now the advantage of Stray over simply applying explainable AI on a single image is that we can observe this or discover these clever hands effects in a systematic manner. Okay, so far I've been showing these images of a horse, but this was basically the prediction strategy of a very simple model, which was composed of 3 layers. But since 2012, there has been a revolution of depth, where people have found out that a very promising way of improving the accuracy of the model at image classification is to take very large data sets and to train very large neural networks. And this neural network can be trained on GPUs. And with this combination of a lot of data and large models, we could achieve very high accuracy could be achieved on image classification. And the question is whether this very large neural network that have been trained on millions of data points are also subject to the clever hands effect. And this is a work from some colleagues by Anders et al., which basically have looked into these questions. And they apply Spray not on the simple neural network, but on this VGG image classifier and on the whole ImageNet data sets. And they found that indeed there are still such clever hand strategies that are being used by these models in some cases. And here we have an image, you have some images of the class garbage truck. And as for the horse case, in the simple model, you can see a reliance of the classifier on some logo at the bottom right, bottom left of the image, which spuriously correlates with images of that class. And you can apply this to one class, but you can also do that on many different classes, and many clever hands effects could be identified on this data set and on this model. And for example, sometimes these effects are very tricky to guess. Here, for example, you have an image, you have some images where that have very tiny rounded corners on every side. And this the presence of these rounded corners correlates again with the class of these images. And again, this can have some, this is a clever hands strategy. We can have some effect on the prediction accuracy. Okay, so basically this was presentation of some of our work on explainable AI. Before finishing, I would like to also talk a bit about the current challenges for XAI. And one big challenge is explanation fidelity. So explanation must accurately capture the decision strategy of the model. And the problem is that we don't know a priori what is the right strategy, what is the actual strategy of the model. So in the context of simple classification, it is relatively easy to evaluate if a model classifies correctly or not, because we can compare it to the labels that are provided by the human. But in the case of explanation fidelity, if you would like to explain the strategy of BGG, for example, we don't know, nobody knows what is the exact strategy that this model is using. It's a huge model. So it's still an open question how to exactly accurately evaluate explanation accuracy on these models. And there are some approaches that have been proposed based on perturbation techniques like pixel fitting. But there are also many different proposals, and it's still an open question. And we also need a bit more theory into this aspect. Then one more challenge is the explanation understandability. And this is mostly when in the case where the decision strategy is complex, mostly because sometimes the task is complex. For example, if a neural network is trained to play Go, it might actually play Go in a way which is actually better than any human would play. And it might be difficult then for the user to be able to distinguish between a correct and a flawed decision strategy, because the model might use things that are correct, but that the user might not know. And this is even the case when the explanation is correct. So this is two explanation fidelity and understandability are two distinct problems. Then there is the question of explanation for validating a machine learning model. And here the idea is that even after applying spray, so you look basically at the explanation on every data point, there might still, in theory, be some hidden clever hints in the model. And basically, strategy that do not occur directly on the data, but that might occur on some other regions of the input space where you have no data, but where there might be some data in the future. And this is especially the case for models with strong ability to generalize. And finally, there is one more current challenge, which is explanation robustness. And I think you are all familiar with the problem that some AI models are vulnerable to adversarial attacks. So some people have been crafting inputs and feeding them to this model to produce incorrect predictions. And sometimes this modification can be very imperceptible and still make a huge difference at the output of the model. And the same is also true for explanations. So there has been some work that have shown that we can craft modification, basically generate inputs that look like normal inputs, but that produce the wrong explanations. And we can do the same with the models. We can also make small modification of the model that then produce explanations that do not correspond anymore to the actual prediction strategy. So this is a concluding slide, just to kind of give a bit of perspective on the relation between explainable AI and our desire to produce more trustworthy models. So you can think of two dimensions: the complexity of the model on the x-axis and the trust. And usually it's very difficult to achieve the two at the same time, because the more complex the model, the more explanations are difficult for the human to understand, the more these models might be vulnerable to adversarial attacks, and the more difficult it is in general to validate explainable AI techniques. So, but still, compared to the classical machine learning model that don't have any explainability, you still get a little bit more of trust. But that's not the only technique. So if you would like really like strongly trustworthy methods, there are other techniques like formal methods that can also achieve this general goal of actually more trustworthy AI. So there are different technologies, and explainable AI is one of them. And what is the specific focus of explainable AI is to take complex model and to increase their degree of trustworthiness. But we are still not at the stage where we can completely trust complex models. Okay, so this is our book on explainable AI that we have published we have edited in 2019, where you see some overview of explainable AI, the different research topics that are being investigated. And I will also invite you to visit our website on explainable AI, which collects some online demos, tutorial, as well as code examples, software, and also our recent papers. And we also recently wrote a review paper, which gives an overview of explainable AI with a focus on deep neural networks. And you can also find it online. So yeah, thank you for your attention. And here are some references.
Yeah, thank you very much for this great talk. Do we have questions? So maybe I will start with one. So, I mean, in this workshop series, we are thinking about trustworthy machine learning, how to measure trustworthiness, how to make sure that methods, models are trustworthy. And we also heard about possible auditing or certification process. And I think also like FDA and other agencies already audited devices which used machine learning for medical purpose. So do you think explanations are important and can play a role in such a auditing or certification process? And if yes, what kind of role do you see explanations can take in this process?
Yeah, so I'm not directly expert on auditing and certification, but I think so there are basically two separate problems. The question of getting standards, which might be enabling application of this model in industry where you want standard, for example, for interoperability, and then the question itself of certification. And yeah, I think so far we are still at the stage where we don't have really like a complete hard guarantee on explainable AI models. On basically explainable AI cannot give hard guarantees on the prediction behavior of the model in future for future data, and it could be potentially part of more general set of methods that would need to that would basically be some kind of benchmark, or and explainable AI would be one possible test, but not the only one.
Yes, yeah, I see, yeah. So we have a question in the Q&A. So how does LRP compare with Google's XRAI algorithm?
So I don't know about the Google XRAI algorithm. I haven't seen this related work. There are many different methods that have been proposed for explainable AI, and usually there are many different factors that needs to be taken into consideration at the same time to get something which works well. And accuracy of the explanation is one of them, as well as speed of explanation, and ultimately how to decide which factor is more important and the other it's more application dependent. But I don't know exactly for what is the comparison with XRAI, because I don't know this related work. But yes, usually when comparing different explainable AI technique, we need to take into account multiple dimensions.
And another question, what are your thoughts on explainability approaches on more complex unsupervised problems like language models, word embeddings? So can we explain something there, or what would we explain?
Yes, so in principle, we can apply explainable AI to unsupervised data. So in fact, we did some work on applying explainable AI to anomaly detection as well as clustering. And at the end of the day, unsupervised learning does some kind of prediction. Basically, it maps some data into some unsupervised structure, which could be a cluster or some degree of anomaly or some likelihood of some point being part of the data distribution. And as long as you have a function that maps the input to something, then this something can be potentially explained in terms of the input features.
We have another one. What's your point of view regarding class discrimination in XAI methods? For example, I read that RedCam has a good reputation in that area. So like about, I think, class discriminativity. When it comes
right. So indeed, that was important issue at some point, which was that depending on which explanation technique you use, and sometimes you have two images with a like let's say with a cat and a dog collocated, and some explanation technique would highlight basically both objects in the image should be relevant for classification, for example. But so this was probably the state of the art a few years ago, and more recently adjustments have been made to explanation techniques to address the problem of class discrimination. And if you look in the special case of LRP, something that strongly helped to produce this class discriminative explanation is to apply a special different rules in different layers. We found out that, for example, using LRP0, which is basically equivalent to gradient times input, in the last few layers helps in that sense, and the more robust LRP rule should be reserved for lower layers.
So I have another one. So last time we talked about backdoors and backdoor attacks or poisoning attacks on machine learning models. So is there like I see some commonalities between clever hunts and backdoors. So do you think we could use also like explanation methods to detect backdoors, backdoor attacks or poisoning attacks, where someone on purpose puts a copyright tag to fool your classifier?
Yes, I mean, definitely explainable AI do reveal some potential backdoors into the model. And I was mentioning this image with the car image that would get classified in the wrong way by adding a copyright tag. But this is rather a coarse type of perturbation, and potentially easily addressable once you have identified the artifacts. You can remediate by showing counter examples. I think that even if you remove all the clever hands effects from the classifier, you might still have backdoors of the more type adversarial, where you can really change every single pixel of the model and of the input to produce a high output score. So it's one approach, be more linked to natural statistics of the data, but there are many other backdoors that probably would not be directly detected using these techniques. And we need other type of approach to guarantee robustness to this more adversarial type of backdoors.
And so what is your feeling like where the field of explainable AI is going? So we saw a lot of progress, a lot of developments on the methodological side in the last year. So what is your opinion on that?
So I think there are many directions in which it could go, and of course the need to make explainable AI more broadly applicable. This is one of them, one aspect I'm specifically interested in is how to make explanation that really explain in a way that the human can understand. So far we have always had a more like technique-centric approach, at least in our attribution-based research, where we would explain in terms of what makes sense from the structure of the function. But in practice, the user might not want to have a heat map, but might want to have some more higher level explanation that make use, for example, of abstract concepts. So for example, here, if you have this direct, the heat map might inform the decision strategy, but you might want some more structured explanation that make use of low-level concepts such as, okay, it's a viaduct because there is an arc, and because of that. So yeah, kind of this explanation user matching. I think it's an important future work.
Do we have any more questions from the audience? So maybe I will take another one. So do you think are there any limits to explainable AI? Do you think there are some functions which are maybe not explainable, or like, for example, chaotic functions which are very hard to explain? Or
yeah, so definitely there are limits in the sense that at some point the explanation has to be delivered to the human. And if we think of AI systems that are actually performing better than the human, for example, playing Go, an explanation might just be not understandable for the human because it's just too complex. The explanation might be correct, but it's just too complex. So fundamentally, I think that there is a limit. So the idea of explainable AI is to put the human in the loop, but we cannot get more from the human than what he's able to give to the feedback to the model.
Yeah. I see. Good. So do we have some more? If not, then I will. Okay, we have. Have you tried to calculate heat maps for images which have been altered with adversarial perturbations?
Yeah, so we tried that at some point. I don't remember exactly what was the outcome. That's definitely an interesting research direction. But very often these adversarial perturbations are actually not interpretable by the human. So if I remember correctly, you would get some kind of noise that would come in superposition to the explanation, and this noise would be actually relatively hard to interpret.
I see. Maybe the last one. Do you think, like, what else could we do with explanations than just looking at them? So what is there anything we could use them for?
Yeah, so that's a very good question. I think we're already using them in some way to validate the model. So basically to decide whether this model should be rejected or whether we should continue to use it. But actually there are a lot more you can do with explanation. And one of them is, for example, to improve the model. So either via direct technique, which would try to define some objective that try to match the ground truth explanation provided by the user and the one that the machine produces. There has been some work in that direction, or indirectly as an iterative process by having this human feedback and then changing the data sets to progressively make it more representative and avoiding these spurious correlations. So yeah, that's I think ultimately why we want explainable AI in this context is mostly to get more like better model, more trustworthy. But there is also an application of explainable AI which I haven't touched on at all in this talk, is explainable AI for understanding something about the data. And that's quite important in scientific application where we have a network of interrelated variables, but the relation between these variables might not be simple linear correlations. It could be something much more complex. And by having this combo of deep neural networks plus explainable AI, you can train a neural network to predict this network of interconnected variables, so predict one given the others, and then you can apply explainable AI to find what are these nonlinear correlation into data, and that has big potential for scientific applications.
Okay, great. So thank you very much for this interesting talk and the great discussion. And yeah, hope to see you soon.
Yeah, thank you very much. Bye-bye.
Thank you very much, Wojciech, and a big thanks also to our speaker, Grégoire Montavon, today. We're going to launch a quick poll to see. We hope you liked it, and please let us know if you did. And in the meantime, let me mention a few things. So we have a webinar on Wednesday on standards and metrics for automated driving, which is part of the ITU focus group meeting on AI for autonomous driving, featuring the ITU Director of Standardization, Dr. Joseph Lee. Additionally, we have the next webinar in the Trustworthy AI series coming up with Jaren Dahl. You can find links for all of this in the chat, as well as on aiforgood.itu.int. And with that, I'd like to once again thank everyone, our speaker, Grégoire Montavon, our host, Wojciech Samek, our partners, sponsors, and co-conveners Switzerland. And I hope to see you all next week.